Hello everyone, I'm Jaren Mane, a PhD student at the KU Leuven, and I'll tell you a little bit about our AAAI paper called The Gradient of Algebraic Mole Counting. This is joint work with my promoter Luc de Raad. An overarching theme in mathematics has been to move away from the concrete towards the abstract. So instead of proving that this equation holds for two real numbers a and b, you can show that it holds more generally for any two ring elements. So in other words, instead of proving a theorem for some specific mathematical object, you can instead prove it for an abstract structure where certain properties hold, such that these properties are the specific ones that you need in this theorem. Now, a natural question is, if this has been so productive for mathematics, can we also apply this to artificial intelligence? In our case, more specifically to probabilistic inference. So let's look at an example. Here we have a small Bayesian network with two nodes A and B, where B is influenced by A. There are many possible inference tasks that you might want to do on this Bayesian network. One example is marginalization, in this case calculating the probability that B takes a specific value, which you can compute by marginalizing A, so summing out over the specific assignments of A. A different one is calculating the most probable assignment, which means that you calculate the maximum over all the possible assignments to A and B. Another one still might be to calculate the entropy of B taking a specific value. Again, you can see this as summing over the assignments of A, in this case with a more specialized product operation, which I'm not going to explain right now. So, as these examples kind of allude, you can see all these inference tasks as basically summing over a set of assignments, and then for each assignment taking a certain product. Kimmich, Van den Broek and de Raad have formalized this as algebraic mole counting. So algebraic mole counting uses a logical formula, and then you aggregate over all the satisfying assignments to this logical formula. There's also a alpha, which basically determines the weight that you give to each variable. And so you can show that to do algebraic mole counting, you basically need a commutative simmering. So these are two binary operations, the sum and the product operations, in combination with a set of properties that need to be satisfied. So most importantly, commutativity, associativity, and distributivity. And this is all you need to do algebraic mole counting, which generalizes all these kind of inference tasks I've done before. So in our paper, we kind of want to extend this view and ask, well, can we also bring this algebraic perspective to probabilistic learning? One important operation in learning is taking the gradient. You can generalize this to simmering as simmering derivations. So simmering derivations are basically functions on your simmering which satisfy two key properties of the gradient, namely linearity and the product rule, sometimes also called the Leibniz rule. And you can show that this is really all you need to do backpropagation. So for any simmering, you can use backpropagation to calculate these simmering derivations. Now for algebraic mole counting, you can show that these simmering derivations can also be seen as taking the algebraic model count of conditioned formulas. So because this algebraic mole count is kind of a linear equation in each variable, taking the simmering derivation means also taking a aggregation over assignments, but now just the assignments where the variable x that you're deriving to is present. And so that's the reason why we define the gradient of the algebraic mole count as this vector of the conditional AMCs towards each literal. Now, what does this give you? Well, we show that this algebraic gradient generalizes many relevant learning tasks. For example, if you use the probabilistic simmering, which means that the sum and product are just the normal sum and product operations, you get a regular gradient, which you can use for gradient descent. Now, if you use the logarithmic simmering, you can compute the logarithm of your gradient by doing backpropagation. And this is often used, for example, to to do expectation maximization. So another example is calculating the conditional entropy towards the different variables. This is relevant if you're learning with information games, for example, namely computing which literal gives you the highest increase in entropy. And another example is for doing gradient estimation, because if you sample and then compute your gradient in a Boolean simmering, you get kind of a state-of-the-art gradient estimator, which has been proposed recently. We make two further technical contributions in the paper. One is on how to efficiently calculate this algebraic gradient. So you can always do this with backpropagation, but if there is further structure in your simmering, you might be able to do it even more efficiently. So the two properties we identify are cancellation and ordering. And if these are present, we show that further optimizations are possible to the backpropagation algorithm. And then a second contribution we make is on higher order gradients. So similar to the algebraic gradient, you can also define an algebraic Hessian or any other higher order gradients or Jacobians. And we show that, well, if you have some very tractable representations, which are specialized data structures that are designed to let you compute the algebraic model count very efficiently, these still remain expensive. So it's not easy to do these. And then I will finish off by showing some experiments. So we implemented the AMC and the AMC gradient in a Rust library. And in this experiment, we show that exploiting the simmering structure does give considerable runtime improvements in practice. So we can show here that the runtime in milliseconds can improve by more than an order of magnitude by exploiting this over just a naive backpropagation algorithm. All right, so that was it. Thank you for listening. And if you want more details, I recommend you to take a look at our paper.